Calculus, Chapter 4, Section 3, How Derivatives Affect the Shape of a Graph. I'm your host, Dr. D. Okay, let's get going here. Alright, now, back in the old days, when we had a function, we had no graphing calculator. We had no computer that could graph for us. We had to simply figure out the shape of the graph by the characteristics of the function. Now, if we understand the characteristics of derivatives and second derivatives, then we get more understanding of the shape of the curve, so we don't just have to plot point by point, but we can know how curves are formed by the characteristics of the function. So let's check this out. First of all, if the first derivative is positive, then f has to be increasing. Why is that? Well, because you have a positive slope in the entire region, so that means your function has to be going uphill. So it could be going up like this, or it could be going up like this, or it could be going up like this. But the point is, it's increasing for sure. Now when we say it's increasing, what we mean is, as we go from left to right, as x gets greater, f of x gets greater. That's what it means to increase. Okay, now, if f prime, if the first derivative is negative, then that means our function has to decrease. So it could be decreasing like this, or like this. But it's decreasing. Now, that doesn't tell us a whole lot. It just says it's going downhill as I go to the right, or uphill as I go to the right. So let's cruise onward to see more things about the function that's going to tell us about the curve. So, second thing, if f prime changes from positive to negative, then f has a relative max at that point. Okay, what does that mean? Okay, if f prime changes from positive to negative, that means the curve goes from a positive slope to a negative slope. Positive here, negative here. Where does it change? Right there. What does it mean about that point? It's a relative max. Now, if my first derivative changes from negative to positive, what happens there? Well, I go negative to positive, negative here, positive here. This is a relative min. Okay, now, what if f prime goes from positive back positive to 0 and then positive again, or negative to 0 and back to negative again? Then what do we have? All right. Here's positive to 0 to positive. That's like the y equals x cubed function. Or negative to 0 back to negative. That would be like y equals negative x cubed. What's going on here? Positive to positive means we have a point of inflection right there. Or negative to negative means we have a point of inflection right there. That's what a point of inflection is. We're going to talk more about points of inflection in a little bit, but that's one thing. If the derivative goes positive to negative or negative to positive, then you have a min or a max. But if it goes from positive to positive or negative to negative, you have a point of inflection. All right, now, Next, if f double prime is positive, then f is concave upward. All right, let's see what this actually means. If f double prime is positive, then f is concave upward. That's what that looks like. Now, notice what's happening. If f double prime is positive, that means f prime is increasing. Because f double prime is the rate of change of f prime. So, what does it mean that f prime is increasing? Well, what's f prime? It's the steepness of f. So, the steepness of f is increasing. So as I go on here, f is getting steeper and steeper and steeper. Okay, now, there's another way. Well, let's look at another thing. Concave upward. Now, concave means it's cupped. And the cup shape is pointing upward. That's what concave upward means. Now, I showed you this where f double prime is positive and f prime is increasing. Now, notice f is also increasing. Well, we could have the same situation if f was decreasing. Here's f decreasing. Now, what's going on? Well, f double prime is still positive. Why? Because what's the steepness of f doing? It's really negative, and it's getting less and less negative as we go. So f prime is increasing. It's going from a big negative to a smaller negative. So this is also concave upward. F double prime is also positive. F prime is increasing, but f itself is decreasing. So this is, notice the first curve I showed you, f is getting steeper, or f is increasing at an increasing rate. Here, f is decreasing at a decreasing rate. Okay, that's f double prime being positive. Now, let's go to f double prime being negative. If f double prime is negative, then f is concave downward. Okay, so here we have f double prime negative, and that means we've got a curve like this. Now let's see, let's decrease it. So we're going to go like this. Okay, now, what's happening here? Well, f double prime is negative, f prime is decreasing. Okay, because remember, f double prime is the rate of change of f prime, and f prime is the rate of change of f. So what's happening here is the function is getting steeper and steeper in the negative direction. That means f prime is getting more and more negative. That means it's decreasing. Now, if f prime is decreasing at a greater and greater rate, then f double prime is negative. What this is saying is this slope is getting steeper and steeper in the negative direction. F double prime is negative. The cup shape is facing downward. This is concave downward. Now, I showed you this decreasing. Can we have this concave downward shape on an increasing curve? Yes, we can. And here it is. Let's just do it down here. Here would be concave downward on an increasing curve. Notice the slope of f is getting more and more shallow. So f prime is decreasing. It's going from a big positive number to a smaller positive number. So it's decreasing. And if f prime is decreasing, then f double prime is negative. And if f double prime is negative, then the cup shape is downward, concave downward. Okay, now, so notice concave down, this is decreasing concave down, this is increasing concave down. All right, now, what does it mean, then, that f double prime changes sign? Okay, f double prime changes sign. That means it goes, the function goes from concave downward to concave upward. Okay, this curve is cupped downward here and it's cupped upward here. What happens when it changes sign is you have a point of inflection. Now, what if it goes from negative to positive? Well, concave upward to concave downward. There's another point of inflection. Concave up to concave down. Now notice I drew both these curves increasing. I could draw both of these curves decreasing also. Concave up to concave down. Concave up to concave down, point of inflection in between. Or concave down to concave up, point of inflection in between. So, if f double prime changes sign, then you have a change in concavity. And if you have a change in concavity, then you have a point of inflection. And notice a point of inflection is either a horizontal tangent or a vertical tangent. Okay, cruising onward. Next, if f prime equals 0 and f double prime is positive, then f must be a relative min. What's that look like? F prime is 0. That means you have to have your slope of the tangent is 0. Now, notice here f double prime is positive. How do we know? Because it's concave upward. Well, notice if I've got the slope of the tangent being 0 and concave upward, I'm guaranteed to have a relative min. Now, if I have nice. All right, we're just going with that. Okay, here I've got slope of the tangent is 0, but it's concave downward. F double prime is negative. What does that mean? Relative max. So this is concave up. This is concave down. This is a relative min, and this is a relative max. This is called the second derivative test. Now remember, the first derivative test said the first derivative is going from negative to positive, it's a relative min. Or the first derivative is going from positive to negative, it's a relative max. Now, why would the second derivative test be simpler? Well, remember, the first derivative test, I have to know the first derivative, and then I have to plug in a point before my critical point and a point after my critical point to see if I'm going from positive to negative or or from negative to positive or positive to negative. So the first derivative test requires 2 points. The second derivative test does not. The second derivative test only requires 1 point. All you have to know is the critical point, and you have to know what the second derivative is right there at that point. You don't need 2 points. Now, when would the second derivative test be inconvenient? It would be inconvenient when it's too much work to get the second derivative. If we've got a polynomial function, the second derivative is easy to get. The second derivative test is a lot easier to tell if you've got a relative min or a relative max in the first derivative test. But if the first derivative test, let's say the function is a rational function and you have to do the quotient rule or something wild like that, then your second derivative test is a nightmare because I don't want to have to do a derivative again of some big, long, nasty fraction. So I'd rather just take the derivative, first derivative, and then check a point before and after and find out what the first derivative is doing. Then I can tell what the function is doing. So that's basically it. Now we're going to apply the things that we learned. Now, I know when we go back to this, oops, wrong direction. We'll edit that out. Okay, notice all this junk that I just threw at you. You've never thought of this stuff before, especially concavity. How are you going to learn this? You have to just stare at it for hours at a time. Just completely go over and over and over it till it becomes second nature. And if you talk to the calculus students from last year, they'll tell you that. It's like after a while it becomes obvious. Right now it's not obvious to you. Now, how do you keep from being one of those people that just gets completely confused and has to drop the course right after Christmas? Well, you get it now instead of waiting till like April to get it. So really dig in and make sure you understand all these concepts. Now, let's take an actual example and work with this stuff. So, all right, here's a graph of the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. And here we have the benefit of a computer that will graph it for us. But remember, back in the 1700s when Sir Isaac Newton developed calculus, they didn't have graphing calculators. They didn't have computers. Actually, back in 1977, when I was taking calculus in college, we didn't have graphing calculators. We didn't have computers. We actually had to do this by hand. Now, you might be saying, oh, well, it's useless for me to learn this crap because I have a graphing calculator. I have a computer. Well, the thing you may have forgotten to take into consideration is that 50% of the AP exam you'll be not permitted a calculator. Not permitted a calculator? Yes. So, you don't want to fail to learn this stuff, and then when you get to the no calculator section, you're grossly bereft. Okay. All right, so let's check this out. Basically, the first question is, where is this function increasing and where is it decreasing? Okay, so let's see where it's increasing and where it's decreasing. So, to know where it's increasing and decreasing, we need its first derivative, which will give us the slope at any point we desire. So the first derivative is going to be 3x to the fourth. Well, that's going to be 12x cubed. And minus 4x cubed is going to be minus 12x squared. And then minus 12x squared is going to be minus 24x. And then the plus 5 derivative of that is 0. Okay, so notice I can factor out a 12x from everything here. And I'm left with x minus, oh wait, I'm sorry, x squared minus x minus 2. Now, x squared minus x minus 2, what multiplies to get negative 2 that adds to get negative 1? Right, negative 2 and positive 1. So this gives us 12x times x. Now let's go plus 1 and then x minus 2. All right, so what does this tell us? Well, if f prime of x equals, nice. We'll edit that out. All right, f prime of x, we want to know where f prime of x equals 0. Well, why do we want to know that? Because that will tell us where the slopes are 0. The slope of the tangent's 0. So where is that going to be? Well, where 12x equals 0, that means where x equals 0. Where x plus 1 equals 0, which means where x equals negative 1. And where x minus 2 equals 0, which is where x equals 2. So here are our critical points. We've got 1 at negative 1. We've got 1 at 0. And we've got 1 at 2, which is way down there. Now, I could plug these values into the original function and get the points. But we still don't know if it's increasing or decreasing on the left or the right of these points. We just know that at these points it goes to 0. So what we're going to do is we're going to find the signs of f prime in these intervals. See, notice I can make a number line here, and I could put negative 1, 0, and 2. What I want to know is, what's the derivative doing to the left of negative 1? Well, if I put in some number that's less than negative 1, then what's 12 times that number? It's a negative number. Negative 1 plus 1, or some number that's left of negative 1, plus 1 will be negative also. And that number minus 2 will be even more negative. So notice I have negative times negative times negative, which is negative. So what does that mean? Well, to the left of negative 1, my function is decreasing. So I could actually say then that on the interval from negative infinity to negative 1, f is decreasing because f prime is negative there. Now, when we get to negative 1, f is neither decreasing nor increasing, it's 0. So that's why I have an open interval here. And negative infinity isn't a number, so clearly you never have a bracket at negative infinity or positive infinity. Okay, so now what happens from negative 1 to 0? Well, we want to check a number that's in between negative 1 and 0. Well, that number would make 12x negative. that number would make x plus 1. Notice if my number is more positive than negative 1, when I add 1 to that, it becomes positive. We'll just leave that alone. And then x minus 2 would be negative. So it would be negative, positive, negative. Well, negative times negative is positive. So that means in between negative 1 and 0 is a positive slope, which means f is increasing. Okay, now let's put in a number between 0 and 2. Well, 12 times that number will be positive, plus 1 on that number will be positive, minus 2, well, it's not as big as 2, so when I subtract 2, that will be negative. Positive times negative is negative. So that means from 0 to 2, f is decreasing again because the slope is negative. Then if we put in a number bigger than 2, positive, positive, positive. So this interval is a positive slope, which means from 2 to infinity, f is increasing. All right, now, let's look at our first derivative test. First derivative test says that the derivative goes from negative to positive at x equals negative 1. What does that mean? Well, if it's going from a negative slope to a positive slope, then that means right here we have a relative min. Now, at negative 1, at x equals 0, we're going from positive to negative. So at x equals 0, we're going from positive to negative. That means right there at that point is a relative max. And then at x equals 2, we're going from negative to positive, and that means at that point we have a relative min way down. Now, if I want to know the coordinates of these critical points, like I said before, all I have to do is plug in negative 1 into my original function, plug in 0 into my original function, and plug in 2 into my original function, and that will give me all three of those critical points. Now, let's look at concavity here. First of all, let's just get rid of all this junk then. Okay, now, concavity has to do with the second derivative. So what we're going to do is we're going to take the second derivative. So let's just take it from right here. So f double prime of x equals 12 times 3 is 36x squared minus 12 times 2 is 24x minus 24. Now notice we can take a 12 out of all three of these. So we end up with 12 times the quantity 3x squared minus 2x minus 2. Okay, so let's go ahead and factor this too. So we get 12 times, let's see if I can just do this. Negative 6, what multiplies to get negative 6, it adds to get negative 2. Nothing. We can't factor this thing. Okay. All right, so now, what we have here is we want to know if these 3 points, these 3 critical points, are mins or maxes. And we're going to use the second derivative test now to find out. So notice, at x equals -1, plug in -1 here, and you get 3 plus 2 is 5, minus 2 is 3. So f double prime equals 3. What does that mean? That means it's positive. So that means it's concave up right here at x equals -1. And that means x equals -1 is a relative min because the first derivative is 0 and the second derivative is positive. That makes it a relative min by the second derivative test. Now, let's take x equals 0. At x equals 0, f double prime is going to equal, oh, I forgot to multiply by 12. Yeah, so technically it's 12 times 3 is 36, but it's still positive, so we don't care. All right, now, when x is 0, then I've got -2 times 12 is -24, so f prime equals -24. What does that mean? Well, that means we have a critical point here at x equals 0, and the second derivative is negative. That means it's concave down right there at x equals 0. That means at x equals 0 we have a relative max because concave down and a critical point. Now at x equals 2, then we've got 3 times 4 is 12, minus 4 is 8, minus 2 is 6, times 12 is 72. So f double prime equals 72. Once again, that means we have concave up at x equals 2, and that means that's a relative min. So that's my second derivative test. And remember, the second derivative test, I just had to test 1 point, and that's it. First derivative test, I had to look to the left and to the right, and that's not all that difficult, but second derivative test for a polynomial function is a lot easier. Okay, now one last thing that we can do here before we cruise onward is find the points of inflection. So, so what we have to do here, to find the points of inflection, we have to find out where the second derivative goes from positive to negative. Now, before we actually do that with a function, I want to show you really what that looks like here. So, let's say I'm climbing a hill, and the hill goes like this. Now I want to know where the point of inflection is. Well, the point of inflection is the point where it goes from concave up to concave down. But if you're hiking up this hill, that point of inflection is basically the point where it starts getting a little easier of a climb. Notice we're climbing the whole way up to here, but down here it's getting steeper and steeper and steeper, and you're going like, oh no, will this never end? Oh my, I'm dying here. But like right when you get to here, it's like, oh, it's not that bad. It's getting better. It's not as steep anymore. Oh, we're almost at the top. So the point of inflection when your function is increasing is the point where it starts getting a little easier. You're not going up quite as steep. You've reached the point of maximum steepness. Now, same thing when you're coming down. If I'm on a roller coaster and I'm at the top and I'm going, oh yeah, this is great, oh, I'm loving it, I'm loving it, I'm loving it. And now all of a sudden, it's going to get to a point where it's not getting steeper anymore. Like this was really fun, and it's getting more and more fun, it's getting more and more fun. And all of a sudden, it's like, oh, we're about done now, we're heading into the station. So the point of inflection, it's concave down to concave up, but the point of inflection as the function's decreasing is the point of maximum steepness. So this is where it's major fun, and then the fun starts to dwindle. Okay, so that's what a point of inflection looks like. Now, let's go to this function and say, okay, where are my points of inflection here? Well, the points of inflection are going to be where f double prime equals 0. So that's where 3x, oops, wrong. 3x squared minus 2x minus 2 equals 0. Those are going to be, those x values will be the locations of the points of inflection. Now, if we were to look at this, just look at the curve. If I start from negative infinity, it's getting less and less steep as I go. So there's no point of inflection there. But then I make the turn and I'm still concave up. Now, where does it become concave down? In other words, let's look a little closer here. We'll zoom in just a little bit here. Okay, so what I want to know is, I'm coming from here and it's getting steeper and steeper and steeper. Now, when does it stop getting steeper? Okay, you decide for yourself. I'm guessing it stops getting steeper right about here. It's getting steeper and steeper. Right about here, it stops getting steeper. Now let's see how close I came. So I'm going to put my, yeah, right about there. Oops, wrong. Ah, nice. Okay. Where was I? I'm saying, yeah, it's hard to tell, but I would say right about there, it's going from concave up to concave down. As it gets steeper, maybe a little higher. Yeah, I'm gonna, oops. Okay, so let's see. Yeah, right there, I'm guessing, by looking at it. Steeper, 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 all of a sudden it stops getting steeper. Now, same thing when we're coming down. It's getting steeper and steeper. Now, when does it start to shallow out? You know, we're going to have to move this again to see a better view of that. But let's deal with this one now. So where is 3x squared minus 2x minus 2 equal to 0? Well, what I want to do is I want to graph 3x squared minus 2x minus 2. Okay. So what I just graphed, that's not what I want to do. Well, okay, what I want to know is, where does this second derivative equal 0? Well, it equals 0 right where it touches the x-axis. So -1, it equals 0, and at 0.613, it equals 0. So -1 and 0.613. Okay, so now where did I guess that the blue, we changed the scale, the blue actually stops getting steep at, oh no, I'm sorry, we're on the red. Yeah, I should get rid of this blue, it's like more confusing than it's worth now. Ah, come on. Okay, so let's get rid of the blue. And all we have back is the red. Okay. So, at x equals -1, let's see what, 3 minus 2, that's not right. Where is 3x squared minus 2x minus 2 equal to 0? Ah. Okay, you work this out on your calculator. What the heck happened to my calculator? Okay.